Welcome to a lesson on Lagrange multipliers with two independent variables. The goal of this video is to determine extrema using the method of Lagrange multipliers. So if we're trying to maximize or minimize f with a constraint g, if they are both differentiable on a specified region and the gradient of g does not equal the zero vector on the curve g of xy equals 0, we'll follow the following two steps to locate the max and mins of f. We'll determine x, y, and lambda based upon the equation the gradient of f is equal to lambda times the gradient of g and the constraint g equals 0. So the result is going to be the following system of equations where the first two involve the partial derivatives of f and g and the third will be the constraint. So the idea behind Lagrange multipliers will have a max or min value when the gradient of f is a multiple of the gradient of g, meaning these two vectors would be parallel where a max or min value occurs. So once we determine x, y, and lambda, step 2 will be to determine which of the above solutions produce a maximum or minimum function value. Let's take a look at the geometry though behind this before we look at an example. So on the right side we see the graph of f, and in red we see the constraint g. And right now we're looking for a minimum value, and you can see that the minimum values are going to occur near the center of this surface, but based upon the constraint g, the minimum value would occur right here, which is also right here on the level curves. So the idea here is the minimum maximum values will occur when these two vectors, where one is the gradient of f and one is the gradient of g, are parallel to each other, meaning they are scalar multiples. And watch as I move the point closer to the minimum, we'll see that happening geometrically. As we move closer, they become parallel. And right at that minimum value, those two vectors are parallel. And the same thing will occur when we're looking for a maximum value. So now the maximum value is over here based upon the constraint in red, and as this point moves closer to that maximum, we'll see those two vectors, which are the gradients, become parallel once again. So this is the idea behind Lagrange multipliers. Let's go and take a look at an example. Here we want to determine the maximum value of f based upon the constraint g. So we're going to create a system of equations by setting the gradient of f equal to lambda times the gradient of g. And the result will be these two equations, and then we have the constraint. So the partial derivative of f with respect to x would be 2x. This is going to be equal to lambda times the partial derivative of g with respect to x. That'll give us negative 2x. For the second equation, we have the partial of f with respect to y. That'll be negative 2y must equal lambda times the partial of g with respect to y, and that would just be 1. And the third equation will be our constraint, y minus x squared equals 0. Now let's see if we can solve this system. Well, by using equation 1, if we divided both sides by negative 2x, well, 2x divided by negative 2x would be negative 1, so lambda would be equal to negative 1. So now using equation 2, if lambda is equal to negative 1, we're going to have negative 2y is equal to negative 1. Well, if we divide both sides by negative 2, we know that y is equal to 1/2. And then finally, using equation 3, if y is equal to 1/2, we'll have 1/2. Let's go ahead and move the x squared over. We'll have 1/2 equals x squared. Square root both sides of the equation. And we have x equals plus or minus 1 over the square root of 2. So this tells us we have 2 points to consider to determine the maximum value of this function based upon this constraint. So one of the points would be positive 1 square root 2 comma 1/2. And the second point to consider would be negative 1 over square root 2. Let's go and determine these function values on the next slide. Okay, so for the first function value, this would be 1/2 minus 1/4. That's going to be 1/4. And for the second point, we're going to have the same function value. We're going to have 1/2 minus 1/4. So this tells us the maximum function value based upon the given function and the constraint is equal to 1/4, and it occurs at two places, at 1 over square root 2 1/2 and negative 1 square root 2 1/2. Let's take a look at this result graphically. So what we're seeing here in purple is the surface generated by f, and then in red we have the constraint. And you can see that when those two surfaces intersect, it produces this yellow curve here, and the maximum value along this curve would be at this blue point here. And if we rotate this around, you can see there would be another maximum function value right in here, which I did not plot. So again, we have the function in purple and the constraint would be in red. So we're looking for the maximum function value that satisfies both of these along this yellow curve. Let's take a look at another example that's a little bit more involved. So we're trying to determine the max and min values of this function based upon the given constraint. So for this problem, we're going to let g of xy equal x squared plus y squared minus 1 equal 0. So we'll set the gradient of f equal to lambda times the gradient of g, which will result in these first two equations. So we'll take the partial derivative of f with respect to x. That'll give us 1 equals lambda times the partial derivative of g with respect to x, which will give us 2x. So for the second equation, we'll take the partial of f with respect to y. That'll be 2. It's going to be equal lambda times the partial derivative of g with respect to y. That'll be 2y. And then lastly, we have our constraint. Now we have to solve this system to determine lambda, x, and y. Using equation 1, we could solve for lambda. Lambda would be 1 over 2x. And then using equation 2, we could solve for lambda, and lambda would be 1 over y. Using these two equations, we know that 1 over 2x must equal 1 over y. If we cross multiply here, we would have y equals 2x. Now we can use this to rewrite equation 3 in terms of one variable. So again, we're going to replace y with 2x. So we're going to have x squared plus, instead of y squared, we'll have 2x squared. That'll be 4x squared. Let's go ahead and move this 1 to the right side. So we'd have equals 1. So we have 5x squared equals 1. So if we divide both sides by 5, we'll have x squared equals 1/5. We square root both sides here. So we have x equals plus or minus 1 over square root of 5. And now that we know x, we can find y from this equation here. Y is equal to 2 times x, so y is going to be equal to plus or minus 2 over the square root of 5. So we're going to have to consider 4 different points based upon the values of x and y, and plug those values into our function f of xy equals x plus 2y. Let's do that on the next slide. Okay, for the sake of time, I've already set this up. Notice it resulted in 4 different points to consider. Here we're going to have 1 plus 4, that's 5 over square root 5. Here we're going to have negative 1 plus 4, that'll be 3 over square root 5. Here we're going to have 1 plus negative 4, that'll be negative 3 over square root of 5. Here we're going to have negative 1 plus negative 4, negative 5 over square root of 5. So the largest value here would be the maximum. So this is our maximum function value, and this would be our minimum function value. If we rationalize this, this would be the square root of 5. Again, this is our max. And this would be negative square root of 5. And this would be our minimum. Let's go and take a look at this graphically as well. So the function is the purple plane and the constraint is the red cylinder. So we're considering the function values along this intersection, which is in green. And we can see here in blue that would be the minimum function value based upon this constraint. That's negative square root 5. And on the other side here, this high point here would be the maximum function value of positive square root 5. Okay, that's going to have to do it for this video. I hope you found these examples helpful.